So let us begin with the sixth problem in the collision mechanics series, and this is problem number 1.170. The problem is stating a ball moving translationally collides elastically with another stationary ball of the same mass. At the moment of impact, the angle between the straight line passing through the centers of the balls and the direction of the initial motion of the striking ball is equal to 45 degree. Assuming the balls to be smooth, find the fraction of the kinetic energy of the striking ball that turned into potential energy at the moment of the maximum deformation. So let us begin this problem by first of all drawing the situation which is described in the problem. So this is how we can explain the situation diagrammatically. So this is the initial condition, or we can say before collision, or that is just at the time of collision. This is just at the time of collision. So now what exactly happens is something which we need to understand to solve this problem. So the collision is always taking place, so it involves three processes. The first thing that involves is the phase before the collision. That is when the two particles are approaching each other. Now once the two particles collide with each other, they bump into each other, deforming each other, such that a point is reached where there is maximum deformation. So at the point of maximum deformation, the two particles start moving with a common velocity. And then after the point of maximum deformation, the particles will start reforming, and as a result of which the two will start moving away from each other, followed by the phase which we say after collision, which is called as moment of separation. So there is an approach followed by deformation, then reformation, and then separation. So we need to understand these four aspects. Now in this problem, the problem is asking us to calculate the common velocity at the maximum deformation. So at the maximum deformation, we can say that the particle has attained a common velocity which we have marked with Vc. Now initially the particle is moving at a 45 degree angle, and hence we can say that if we break the component of u, so we will have a component in this direction which is u cos 45 degree, so u by root 2, and then in this direction we will again have u by root 2. Now since this is the line of impact which we have marked with x-axis, so this is the line of impact. So the velocity in the y direction, or velocity perpendicular to the line of impact, will remain unchanged, and a common velocity will be attained in the line of impact. So this is the moment at maximum deformation. At maximum deformation, the conceptual clarity needed is that at maximum deformation the particles will be moving with common velocity which we have marked with Vc. So now the first thing that we do is we apply momentum conservation along x-axis or in the line of impact, and hence we say that initial momentum in the x direction is equal to final momentum in the x direction, and hence we write it as m u by root 2 equals 2m times Vc, or the common velocity in the x direction, and from here we can say that the common velocity in the x direction is u upon 2 root 2. So this is equation number 1 that we have. Now the problem is asking us to calculate the fraction of the kinetic energy of the striking ball that turned into potential energy at the moment of maximum deformation. So over here we calculate kinetic energy initial. So kinetic energy initial equals half m u square, and then we write kinetic energy final. So now the final kinetic energy is going to be very interesting. So this particle which we refer as particle 1, which collides with the particle 2. So this particle 1 is having velocity in the two directions. So one is in the x direction and the another in the y direction. While particle 2 is having velocity only in the x direction. So if we write final velocity for particle 1, so final velocity for particle 1 can be written as, so common velocity u by 2 root 2 I cap followed by u by root 2 j cap. So if we calculate the magnitude of this velocity, so we say square of this term followed by square and then square root. So since while writing the kinetic energy term, we will only be needing v1 square. So v1 square can be written as u by 2 root 2 squared plus u by root 2 squared. So this is the expression which is going to be used here while we write final kinetic energy. So we write over here half m v1 square. So v1 square we are mentioning as u by 2 root 2 square plus u by root 2 square, and followed by this we have another particle of mass m having speed u by root 2 squared. So this entire expression is the final kinetic energy of the particle which we have at maximum deformation. So now the loss of kinetic energy. So if we calculate the loss of kinetic energy, so the loss of kinetic energy can be calculated as initial kinetic energy minus final kinetic energy, and hence we subtract the two terms. So we have a half mu square as this one, and then we subtract these two terms involved, and on solving this part we obtain 1 by 8 times of mu square. Now this is going to play a very vital role as we solve ahead, because the problem is asking us to calculate the fraction of kinetic energy loss. So fraction of kinetic energy lost. So if we calculate eta, then we say loss in kinetic energy by original. So loss of kinetic energy by original value of kinetic energy, and we obtain a value eta of 0.25, or if we calculate in percentage it is a 25% loss. So this is the final answer for this problem number 1.170.